My name is Andisiwe Ngayo from Zomsha High School. Welcome to the ECDOE Broadcast Studio. Today's lesson is about the rate and extent of a reaction. I'll be covering this topic for your full understanding. First of all, you need to know how to define a rate and an extent of a reaction. You define the rate of a reaction as the change in concentration of the reactants or the products per unit time. You also need to be able to calculate the reaction rate from given data. We measure the reaction rates using a timer or a stopwatch. So you can measure the change in concentration of the substance being produced or the reacting or the volume, or you can measure the concentration per unit time. You can also measure the volume per unit time. Questions may also include the calculations of rates in terms of the change in mass, volume, moles per unit time. We'll also list the factors that affect the rate of reaction, that is, the nature of substance reacting, the surface area for solids, the concentration, the pressure for gases, as well as the temperature and the catalyst. We will also explain the terms of the collision theory, how about each factor affecting the rate of reaction, also using Maxwell distribution curve. We first define what activation energy is. In order for a reaction to take place, reacting particles need to react. They need to reach a certain amount of energy. This minimum energy that the reaction needs in order for it to take place, we call it the activation energy. At the state whereby the bonds are breaking, because in order for a reaction to take place, molecules need to be in their atomic state, meaning that old bonds need to break and new bonds need to form. At this state whereby the old bonds are breaking and at the same time the new bonds are forming, we call this the activated complex. It is an unstable, high energy state of transition from reactants to products. We will draw, interpret, and fully label the sketch graphs on potential energy versus the cost of reaction of catalyzed and uncatalyzed, endothermic or exothermic reaction. Just a quick reminder, an endothermic reaction is a reaction that whereby more heat is absorbed than heat that is actually released during bond formation. And then an exothermic reaction is a reaction whereby more heat is released than energy that is actually absorbed at the beginning of the reaction when the bonds were breaking. However, whether the reaction is exothermic or endothermic, it means that there was a bond breaking, and during bond breaking, there was an absorption of energy. And there is a bond formation, and during bond formation, there is a release of energy. We explain using the collision theory. We say, number one, the reacting particles, they need to be in atoms and they need to collide with each other. The particles must have sufficient kinetic energy and must be correct orientated in order for reaction to take place. Now, bonds in the original molecules must break and new bonds must form. Electrons must be rearranged in order to form new bonds. In order for effective collisions to take place, if you can look here, we have got a carbon, which is the black substance representing the carbon. The small white circles represent the hydrogen atoms. They are now bonded to this molecule. Now, what happens is when we say correct orientation, this gray represents a chlorine atom. This white represents a hydrogen atom. Now, this is a correct orientation if the hydrogen atom is the one approaching this carbon-carbon atom. Therefore, we say that this is an effective collision because they are correctly oriented, meaning that the reaction will take place, the product will be produced. However, if the chlorine atom from the hydrogen chloride molecule is the one that is approaching this carbon-carbon double bond, then we will say this is not the correct orientation, hence the X there, which means that the effective collision will not take place. Also, if this chlorine atom is the one attacking the hydrogen atoms from this molecule, then again, this is not an effective collision. And again, if the hydrogen atom is approaching another hydrogen atom, the correct orientation means that the hydrogen must be the one colliding with these carbon atoms. Then we say they are correctly oriented. In order for the collisions to be effective, remember, collisions do take place based on the kinetic molecular theory of matter, which says that all particles are in random motion and therefore they are colliding with each other. However, in order for it to be an effective collisions, they need to collide with sufficient kinetic energy and the colliding particles need to be correctly oriented. Measuring the rate of reaction, like I said, it takes time. You measure using a stopwatch. This is a stopwatch. So you have got your reaction vessel whereby the reactants are poured into. How do you measure the rate of reaction? You can measure the rate of reaction using your stopwatch. Having your reaction vessel, you pour in your reactants into the reaction vessel. The reaction vessels, you can see there is a connection with a plunger to the syringe. Now what happens is as the reaction takes place, the gas will escape from the reaction vessel, go through the gas syringe. The plunger from the syringe will move backwards. You can measure the rate of reaction by looking at the time it takes for this plunger to move from this point to this point. Therefore, you are measuring the rate of the reaction. In this case, we are measuring the volume of the product produced, which is a gas molecule being produced. Therefore, the rate of reaction graph will begin from the point of origin, which is 0, because at the beginning we had 0 volume of the gas. Now, as time goes by, the volume increases as a function of time. Now, at this point whereby the graph gets to be level or gets to be flat, we say that the reaction has come to an end. Why? Because there is now no change in the amount of volume being produced. If we had values here, this is at a constant volume. And as you know from your mathematics, that the function of this volume of gas versus time graph, the gradient here at this point is equal to 0. And we said that the rate of the reaction is the change in concentration over the time. Therefore, what is the relationship between the rate of the reaction and time? It is actually that as the reaction takes place, the rate of reaction decreases over time. You can also measure the rate by measuring the reaction vessel, which is, in this case, you are measuring the system, which is the beaker that contains, or the Erlenmeyer flask that contains the reactants. You can see that this is put on top of a weighing balance. So it is giving you a reading here. So what happens is, as these particles are reacting, therefore, there is a gas that is actually released. Now what happens is the reactant amount is going to decrease over time. So if that is the case, this means that now you can close this with a cotton wool so that the gas does not escape. If the gas does not escape in this case, however, even though it does not escape, the amount of the reactants is going to decrease because product is being formed. Now the graph is starting at a higher peak and it decreases over time. What does this tell us? This tells us that this is a graph that shows the amount of the reactants over time. So this is the mass of the flask and the contents at the beginning, and then it decreases over time. So again, if you draw your tangent between the volume versus time graph, what you're going to observe is that it gets less steeper and less steeper as time goes by. Now, what does that tell you? That tells you that the rate of the reaction is decreasing. As you can see, the initial steepness of the gradient indicates the higher reaction rate as the gas forms. But as you can see that if you draw your tangent here, the graph actually gets less steeper, meaning that the rate of the reaction is coming to an end. When does the reaction end? It ends when the graph starts to get what? Level. It gets horizontal. Remember, the gradient of this graph is gonna be equal to 0 if your shape is like this. Measuring the rates of reaction, we can actually also measure using by observing from the reaction vessel. If you observe from the top of the flask, you can put an X, that is a reaction whereby a precipitate is formed. For example, in the reaction of sodium thiosulfate with hydrochloric acid, sulfur is released as a precipitate. Sulfur is yellow in color, and therefore, if you have a sheet of paper, white paper that is labeled with a black X, you put your reaction vessel on top of that and observe from the top view. What will happen is, as time elapses, that X will now become invisible because of the formation of the precipitate, which is the sulfur, which is yellow in color, and therefore eventually you will not be able to see the X anymore. You can also measure the rate of the reaction by using a stopwatch as to how long did it take as you were observing the X to actually disappear. Some of the factors that affect the reaction rate, like I mentioned, include number one, the nature of the reacting substances, the surface area, also the concentration, the pressure for gases, temperature, as well as the use of a catalyst. Using Maxwell-Boltzmann distribution curve, we can look into the effect of the temperature on the rate of reaction. If you can see from this graph, remember, learners, that a measuring of temperature is actually a measurement of the average kinetic energy of the particles. Now, what does that say? Remember, the particles need to have climb up a mountain hill, which actually states that they need to have an activation energy, meaning that they need to have a minimum energy that is needed for a reaction to take place. If you look at the two graphs that we are having here, number one, if you look at the graphs that we are having here, number one, these are the number of molecules versus the molecular energy. What is happening? The dotted line graph is more skewed to the left. What does that mean? The area under this graph at this point is the greatest. That means that more particles are having less kinetic energy. That means that more particles have got less kinetic energy that is less than the activation energy, because this is the activation energy. Also, if you observe the area under the graph at this point in time, these are the few particles that have got kinetic energy that is equal to, because this is where your EA is, which is activation energy. That is, the fewer particles have got kinetic energy that is equal to or greater than the activation energy. However, if you look at the solid line graph, the solid line graph indicates that the graph is less, the peak decreases there. That means that the graph is more skewed to the right. Therefore, this results in this gray shaded area, which means that there are more particles because this area is now greater. That means there are more particles having kinetic energy that is equal to or greater than the average kinetic, greater than the activation energy. This actually means that more particles will collide with sufficient kinetic energy per unit time. Therefore, more effective collisions will take place. Hence, the rate of the reaction will increase. Again, the effect of the increase in temperature between the graphs labeled T1 and T2, which graph has got a higher temperature. As you can see, it's T2 because the area under the graph, this is the activation energy. This means that there are more particles having kinetic energy that is equal to. This means that there are more particles having kinetic energy, average kinetic energy, that is equal to or greater than the activation energy. However, if you look at T1, the graph has got a higher peak, and therefore there is a less surface area, there is a less area under the graph there, which means that there are fewer particles having kinetic energy that is equal to or greater than the activation energy. You will be asked to calculate the rate of reaction. The examiners will give you the measurements. If you are asked to calculate the rate of the reaction using concentration versus time, the concentration versus time will, for the reactants, you will have to include the minus sign if you are calculating for the reactants. Why? because throughout the course of the reaction, the concentration of the reactants that you start with is actually bigger. However, as the reaction takes time, the concentration of the products decreases over time. This means that you're going to have less amount of the concentration of the reactants in the final time. Remember, delta means change. So change is always final minus initial. Therefore, the minus sign is to cancel that negative number you would get there so that your rate does not become negative. We include these negative signs in our calculations if the rate was measured using a reactant. Therefore, we include the negative. However, if the rate was measured using the products, there is no need for the negative sign because the concentration or the volume or the mass or the number of moles of the products finally will always be greater than what was there initially, because at the beginning of the reaction you start with 0 products but you end with a larger amount. The unit for the rate of reaction depends on what you were measuring against time. So the unit always comes at the question, with the question. The effect of a catalyst. How does a catalyst affect the rate of the reaction? A catalyst does not tamper with the activation energy of the particles. However, it creates an alternative pathway. Think of it this way. The reactants had to climb this mountain hill in order for them to form the products at this other end. So if you have got a catalyst now, the catalyst comes and provides an alternative pathway, which is denoted by these dotted lines. So this means that now the particles don't have to all go through this mountain hill. If there were fewer particles that could go up there, now there are going to be more particles that can actually form part of the reactants, as more particles will be able to climb this hill that is actually of less kinetic energy. This is a pathway created by a catalyst. Remember, a positive catalyst is a substance that does not form part of the reaction. However, it assists the reaction to take place. The catalyst will not by any means affect the activation energy or the kinetic energy of the particles. However, when we explain it, we say that an introduction of a catalyst introduces an alternative pathway for the reaction to take place. Therefore, more particles with sufficient kinetic energy will collide, and therefore the rate of the reaction will increase. During the collisions, the particles need to collide having correct orientation. As we have explained, if you can see from this slide, you can see that the oxygen, the chlorine atom is the one, this chlorine atom is the one approaching the oxygen atom. Therefore, this collision is not effective because afterwards they go in their separate ways, still intact, therefore no product formed. If the hydrogen atom is the one approaching the oxygen atom in the water molecule, then this collision will result in an effective collision because now the hydrogen atom is attached to this oxygen, as you can see, and then the chlorine atom is left without a hydrogen. It proceeds in the opposite way to that, and therefore this is an effective collision because a new compound is formed. Therefore, a product has been formed. Explaining using the Maxwell-Boltzmann distribution curve, a catalyst, effect of a catalyst. Effect of a catalyst means that because we had a new activation energy, which is the lowered one, if the catalyst is there, the activation energy will be lowered. As this is the energy, if you move from left to right, it increases. So when you bring a catalyst in, the activation energy will now start at this point. This allows the particles that were also in this area, the brown area, that could not have sufficient kinetic energy to react, to be formed, to now be able to form part of the product. Unlike the green part, which was without a catalyst, only these few particles would have been able to react. Therefore, this increases the chance of effective collisions per unit time. So now, instead of the reaction taking longer, it actually takes a shorter time. The effect of a concentration to the rate of reaction. Now think of a concentration as Concentration is the measurement of the amount of particles of a substance per unit volume. Then if a substance is highly concentrated, it simply means there's more particles of the substance than the particles of the solvent. If your solvent is water, your substance is sodium chloride. A highly concentrated solution would have more particles, which is the black line, black dots represent the sodium chloride. There will be more particles of the sodium chloride than the solvent, in this case, which is water. However, if it is dilute, which simply means there is fewer particles of the sodium chloride than the solvent, in this case, which is the water. Therefore, if you have more particles per unit volume exposed, this means that the reaction rate will actually be faster. Why? We explain it saying with a greater surface area or with a greater concentration, more particles are exposed per unit volume. Therefore, more particles will have correct orientation and therefore more effective collisions per unit time. The reaction rate increases. We explain it similarly to the effect of concentration. At a higher concentration, there are more particles per unit volume. As you can see, the key word here is on the effect. So if you are affecting the concentration, if you increase concentration, you are increasing the number of particles per unit volume. If you are increasing the surface area, you are increasing the number of particles exposed with correct orientation per unit area. The effect of concentration using the Maxwell-Boltzmann distribution curve is actually explaining if you have got a number of molecules versus the kinetic energy. The part whereby the graph is having a higher peak is the one that is having a higher concentration. Why? Because there's a higher number of molecules per unit volume. Therefore, the area under the graph means that the particles that have got the kinetic energy that is equal to or greater than the activation energy has increased. So the area under the graph has increased. Therefore, an increase in concentration increases the number of particles with sufficient kinetic energy that are exposed per unit volume with correct orientation. Therefore, the rate of reaction increases. In summary, what we are now saying is that the factors that affect the rate of reaction include the nature of the reactants, this temperature, the catalyst, the concentration for the reaction, and also the pressure for gases. If you increase those, you increase the rate of the reaction. Remember, in order for a reaction to take place, average kinetic energy of the particles need to be equal to or greater than the activation energy. Particles also need to be correctly orientated. Also, this means that in order for effective collisions to take place, particles don't just collide, but they need to have sufficient kinetic energy. And remember, the effect of the catalyst will not by anyhow increase the kinetic energy of the particles. However, it will offer an alternative pathway with lowered activation energy. This is very key for you to understand and to actually be able to apply it. However, the number of particles with sufficient kinetic energy to react will be available in the presence of a catalyst. We have come to the end of our lesson. You can leave your questions on the comments. Don't forget to leave the name of your school so we can give shout outs. Please share, recommend, and subscribe to our YouTube channel. Thank you for watching. See you on our next lesson.